Good evening. I'm Siddharth, 4th semester mechanical engineering, and today I will be talking about flow over an aerofoil. An aerofoil is a two-dimensional cross-section of an aeroplane wing. Alternatively, an aerofoil can be thought of as an infinite wing of constant shape. The wings of birds were the original inspiration for the design of aerofoils. However, it was not until 1799 that engineer George Cayley carried out the first methodological study on the performance of aerofoils. His publications on aerial navigation in 1810 marked the beginning of the science of aerodynamics. Since then, numerous fixed and variable aerofoil profiles have been developed, inspired by fish as well as birds, to optimize lift, drag, and stalling characteristics over a wide range of speeds and through a variety of fluids. A fluid flowing around the surface of an object exerts a force on it. Lift is the component of this force that is perpendicular to the oncoming flow direction. It contrasts with the drag force, which is the component of force parallel to the flow direction. Lift conventionally acts in the upward direction in order to counter the force of gravity, but it can act in any direction at right angles to the direction of flow. If the surrounding fluid is air, the force is called aerodynamic force. In water or any other liquid, it is called hydrodynamic force. Bernoulli's theory of flight. The theory of flight is often explained in terms of the Bernoulli's equation, which is the statement of the conservation of energy. It states that for a non-viscous incompressible fluid in steady flow, the sum of pressure, potential, and kinetic energies per unit volume is constant at any point. In other words, ignoring the potential energy due to altitude, when the velocity of a fluid increases, the pressure decreases by an equivalent amount to maintain the overall energy. This is known as the Bernoulli's principle. As you can see here, aerodynamic lift can be explained by Bernoulli's conservation of energy law. According to Bernoulli's principle, the air passing over the top of an aerofoil or wing must travel further and hence faster than the air traveling the shorter distance under the wing in the same period. But the energy associated with the air must remain constant at all times. The consequence of this is that the air above the wing has lower pressure than the air below the wing, and this pressure difference creates lift. However, it is unfortunate that Bernoulli's principle does not explain how an aeroplane can fly upside down, nor does it explain how aircraft and other structures with flat plate wings or even kites and paper aeroplanes can fly or remain airborne. This is where Newton's law comes to the rescue. Newton's theory of flight. Isaac Newton did not propose a theory of flight, but he did provide us with the Newton's law of motion, the physical laws which can be used to explain aerodynamic lift. Newton's second law states that the force of an object is equal to its mass times its acceleration, or equivalent to the rate of change of momentum, that is, F is equal to ma. In other words, whenever there is a change of momentum, there must be a force causing it. In this case, since momentum is a vector quantity, the change in direction of the airflow around the wing must be associated with the force on the volume of the air involved. Newton's third law states that to every action there is an equal and opposite reaction. As mentioned before, Newton's third law states that to every action there is an equal and opposite reaction. This means that the force of the aerofoil pushing the air downwards, creating the downwash, is accompanied by an equal and opposite force from the air pushing the aerofoil upwards and hence providing the aerodynamic lift. It is thus the turning of the airflow which creates the lift. Lift occurs when a moving flow of air is turned by a solid object. The flow is turned in one direction and the lift is generated in the opposite direction, according to Newton's third law of action and reaction. For an aircraft wing, both the upper and lower surfaces contribute to the flow turning or the downwash. Angle of attack. The angle of attack of a turbine blade is the angle between the direction of the apparent and relative wind and the chord line of the blade. For an aircraft wing, it is the angle between the direction of motion of the wing and the chord line of the wing. At very low angles of attack, The airflow over the aerofoil is essentially smooth and laminar, with perhaps a small amount of turbulence occurring at the trailing edge of the aerofoil. The point at which laminar flow ceases and turbulence begins is known as the separation point. Increasing the angle of attack increases the area of the aerofoil facing directly into the wing. This increases the lift, but it also moves the separation point of laminar flow of the air above the aerofoil part way up towards the leading edge, and the result of the increased turbulent flow above the airfoil is an increase in the drag. Maximum lift typically occurs when the angle of attack is around 15 degrees, but this could be higher for specially designed aerofoils. Above 15 degrees, the separation point moves right up to the leading edge of the aerofoil, and laminar flow above the aerofoil is destroyed. The increased turbulence causes the rapid deterioration of the lift force, while at the same time it dramatically increases drag, resulting in a stall. This graph shows the lift and drag at different angles of attack experienced by a Clark-White aerofoil, a type of aerofoil widely used in general purpose aircraft designs. The angle of attack is plotted on the x-axis, and the drag coefficient and lift coefficient are plotted on the y-axis respectively. The blue line represents the lift, while the red line represents drag. It is seen that when moving through the air at constant speed, as the angle of attack is increased, both the lift and the drag increase until the aerofoil reaches a critical angle, when then the lift suddenly falls away and the aerofoil begins to stall. In this case, as the angle of attack approaches about 20 degrees. Drag, however, continues to increase as the angle of attack increases. Since the lift generated by an aircraft wing is proportional to the angle of attack and also to the square of the aircraft speed, the same lift can be accomplished by flying at a higher speed with a lower angle of attack. Reducing the angle of attack also reduces the induced drag due to turbulence, thus enabling greater aerodynamic efficiency. Let us talk about the aerodynamic drag components. Drag is the force experienced by an object representing the resistance to its movement through a fluid, sometimes called wind resistance or fluid resistance. It acts in the opposite direction to the relative motion between the object and the fluid. The aerodynamic drag forces experienced by an aerofoil or aircraft wing while moving through the air with a constant angle of attack as its airspeed is increased. The total aerodynamic drag is the sum of the following components: the induced drag, pressure drag, friction drag, profile drag, interference drag, and wave drag. Induced drag. Due to the vortices and turbulence resulting from the turning of the airflow and the downwash associated with the generation of lift, it increases with the angle of attack and is inversely proportional to the square of the airspeed. That means decreases as aircraft speed increases and the angle of attack is reduced. Induced drag associated with high angle of attack needed to maintain the lift is dominant at low airspeeds. Form drag, or also known as pressure drag, it is due to the size and shape of the aerofoil. It increases with the square of the airspeed. Streamlined shapes designed to reduce this form of drag. Well, the next one is friction drag. Friction drag arises from the friction of the air against the skin of the aerofoil moving through it. It increases with the surface area of the aerofoil and the square of the airspeed. The profile drag or the viscous drag is the sum of friction drag and form drag. The parasite drag, or also known as the interference drag, is incurred by the non-lifting parts of the aircraft such as the wheels, the fuselage, the tail fins, the engine, the handles and the rivets. Increases with the square of the airspeed. Parasite drag becomes dominant at higher airspeeds. The final form of drag is the wave drag. This is due to the presence of shock waves occurring on the blade tips of aircrafts and projectiles. Associated with passing the sound barrier, it is a sudden and dramatic increase in drag which only comes into play as the vehicle increases speed through the transonic and supersonic speeds. It is independent of viscous effects. This graph shows us how the different drags vary with increase or decrease in airspeed. The drag component is plotted on the y-axis and the airspeed is plotted on the x-axis. As you can see, the total drag first decreases with increase in airspeed until it reaches a point of minimum drag and then continues to increase with increase in airspeed. You can also observe that the parasite drag is directly proportional to the square of the airspeed and the induced drag is inversely proportional to the square of the airspeed. The profile drag, however, increases with constant increase in airspeed. Practical examples of flow over an aerofoil and the principal and basic forces involved are that of an aircraft wing and wind turbines, which are both dependent for their action on the flow of air around the aerofoils. Therefore, I would like to conclude by saying that the flow over an aerofoil basically refers to the field of science known as aerodynamics and is a very important part in our day-to-day life. Thank you.